Next topic sa open cycle gas turbine plant is the methods of improving our thermal efficiency. So it is impossible for a system to achieve 100% efficiency. Pero hindi ibig sabihin nun, hindi na natin pwedeng improve. Okay? And we have three methods of improving our thermal efficiency. Una is intercooling, ikalawa ay reheating, and the third is regeneration. Bakit pa natin kinakailangan i-improve pa si efficiency kung sinabi na natin na hindi pwedeng ma-achieve yung 100? So increasing the efficiency will lessen the environmental impact kasi it requires less resources. Kasi mas efficient yung system, di na kakailanganin pang gumamit pa ng resources or external resources. So first is intercooling. Ano nga bang intercooling? Compressor utilizes the major percentage of power developed by the gas turbine. The work required by the compressor can be reduced by compressing the air in two stages and incorporation a intercooler between the two. So ito yung LPC, low pressure compressor stage. Tapos sabi nga dito, in between the two ay ito yung intercooler natin. Tapos nito ay high pressure compressor stage papunta sa ating turbine. Ito, ano ba sabihin ng intercooling talaga? It is the stage of multi-compression in a gas turbine. After the compression of gas in the first compressor, its pressure and temperature are increased, and this gas is passed through the intercooler, where its temperature decreases. The intercooling process is done by passing an extra amount of water or air. So, bakit kinakailangan o bakit ginamit si intercooling? Intercooling in gas turbine is one of the methods to improve nga, di ba, the efficiency of the gas turbine. Dahil it increases the network output by reducing our work sa system natin. Required to drive compressor by carry out the compression air in two stages. Okay? So next, we have reheating. Reheating, the output of gas turbine can be improved by expanding the gases in two stages with a reheater within two. Okay. The high pressure turbine drives the compressor, high pressure turbine compressor, and the low pressure turbine provides useful power output. Okay. Yung ating reheater. So, heating in a gas turbine. Ano bang reheating? Muling iinit yung alin? Yung ating gases sa ating system. So, bakit nga? Kasi it increases the thermal efficiency. The heating is applied in a gas turbine in such a way that increases the turbine work without increasing the compressor work. Patataasin mo yung work ng turbina without increasing the compressor, the work of the compressor, or melting the turbine materials. Isipin mo, iinit mo pero hindi matutunaw yung nasa loob ng system natin. Okay? When a gas turbine plant has high pressure and low pressure turbine, a reheater can be applied successfully. Okay? Okay. At ang last method for increasing our thermal efficiency is regeneration. Regeneration, the exhaust gases from the turbine carry a large quantity of heat with them since their temperature is far above the ambient temperature. They can be used to heat air coming from the compressor, by reducing the mass of fuel supplied in the combustion chamber. Okay. Regenerative cycle has more efficiency than simple cycle at lower pressure ratio. Okay, discuss natin ito mamaya. Dito muna tayo kay regeneration. Regeneration is a thermodynamic process that utilizes the remaining energy in the exhaust gases from the gas turbine to heat the air entering to the gas turbine. Okay, so bakit nga ba nakataas ng thermal efficiency? Regeneration increases the thermal efficiency since more of the heat flow into the cycle occurs at higher temperature. Kasi i-regenerate, muli natin gagamitin yung remaining energy in the exhaust gas, in the exhaust gases. Regenerative has more efficiency, di ba? Bakit nga? More than, mas mataas sa simple cycle? Kasi yung thermal efficiency ni regenerative is mas mataas dahil ginagamit natin yung ating remaining energy sa ating exhaust gases. Above certain pressure ratio limit, the efficiency of cycle drops since the case regenerator will pull the compressed air instead of heating it. Next. And this is the second type of gas turbine power plants. It is the closed cycle gas turbine power plant. In this type of power plant, the mass of air is constant or another suitable gas used as working medium. Okay, take note, the mass of air is constant or another suitable gas used as working medium. Circulates through the cycle over and over again. Kaya close. Paulit-ulit lang, sarado lang. The compression and expansion process remain the same, but the combustion process is replaced by a constant pressure heat addition from an external source. So, okay. And the exhaust. Okay. And the exhaust process is replaced by a constant pressure heat rejection process to the ambient air. So, nabanggit dito na the combustion process is replaced by a constant pressure heat addition. Diba? Kasi a closed cycle gas turbine is a turbine that uses gas for the working fluid as part of a closed thermodynamic system. Okay? And heat is supplied from an external source. Such recirculating turbines follow the Brayton cycle. Dito siya nagkakaroon ng heat addition sa heat exchanger number 1 natin. Okay? And we have the TS diagram for closed loop cycle turbine. Okay. Process 1 to 2, the air is compressed isentropically, meaning the entropy of the fluid or gas remains constant isentropically. From lower pressure P1 to the upper pressure P2, temperature rising from T1 to T2. Okay. Heat, sa process 2 to 3, heat flows in the system increasing its volume V2 to V3 and temperature T2 to T3. Pressure remains constant at P2. Heat received is equals to mass times specific heat multiplied to the quantity T3 minus T2. Sa ating process 3 to 4, the air is expanded isentropically from P2 to P1. Again, isentropically constant enthalpy. And temperature T3 to T4, no heat flow occur. And process 4 to 5, heat is rejected from the system as volume decrease from volume 1 to from volume 4 to volume 1 rather, and temperature from T4 to T1. Pressure remains constant at P1 and heat rejected is equals to mass times specific heat times quantity T4 minus T1. Nandito yung ating PV and TS diagram. So, okay. The heating of the gas is done at constant pressure. Okay. Sabi dito, P1 to process 1, process 2, constant pressure. Here, as the pressure is constant, so P1 is equals to P2. And the temperature increases from T1 to T2. Ayan, T1 to T2. The entropy of gas increases during this process. Ayan. Kasi nag-increase yung temperature 1, temperature 2, so as our entropy. Okay, from process 2 to 3, and to 3. Isentropic expansion of the gas takes place in the turbine. Bakit nga ba turbine? Kasi sa ating schematic diagram, 2 to 3, dito ang ating turbine o heat exchanger. 2 to 3. Here, the pressure drops from P2 to P3. And P2 to P3. Nag-decrease yung ating pressure. And the volume increases naman. From V2 to V3. So, V2 to V3. So, bumaba yung pressure natin. Pumula natin sa taas, punta pa baba. And yung volume natin is next. Tumaas din ang volume. Pumula dito, nag-move, right. Okay. In TS diagram, the entropy remains constant, but the temperature dropped from T3 to T4. Okay. From process 3 to 4 naman, cooling of gas is happening at constant pressure. Constant pressure. In PV diagram, the pressure remains constant, kaya pressure 3 is equals to pressure 4, and the volume decrease from volume 3 to volume 4. Okay? And sa process 4 to 1, bumalik. Isentropic compression takes place in the compressor. Obviously. In PV diagram, the pressure increases from P4 to P1, and volume decreases from volume 4 to volume 1. And volume 4 to volume 4 to volume 1. Ayan. Okay. At sa TS diagram naman natin, the entropy remains constant. 4 to 1, and constant lang siya. And the temperature increases naman from 4 to mas papunta sa temperature 1. The initial temperature of the gas, it means the gas attains its initial temperature. Bumalik siya sa dati niya. Oh, mabalik, no? So we have the performance. Okay, so let's proceed to the performance of a standard Brayton cycle, or yung cycle na ginagamit natin sa ating gas turbine. Okay, so we have the compressor here, we have the combustor, we have the turbine generator. Sa ating compressor, nandito yung process 1 to 2, compressor 1 to 2, and from combustor to turbine 2 to 3, turbine to compressor is 3 to 4. 3 to 4, and 4 to 1 is turbine to compressor, pabalik. Okay. And of course, familiar na tayo sa ating TS diagram ng ating gas turbine cycle or Brayton cycle. So, first formula, PV and T relation in isentropic compression, process 1 to 2. Process 1 to 2, compressor. Okay, P1, V1, okay, ito yung equals P2, P2, and T natin. T2 over T1 is equals to P2 over P1, K minus 1 over K, and then T2 over T1 plus B1 over B2, K minus 1. Okay. The R is the pressure ratio, is equals to P2 minus P1 plus P3 all over P4. Sorry, P2 all over P1 equals P3 all over P4. Okay, so ano papansin dito? Ito yung ating ideal gas. Sinunod lang siya sa ating ideal gas. Okay, and the compressor work. Okay. Process 1 to 2 pa rin tayo, kaya nandito yung ating compressor work. Work of the compressor is equals to mass times specific heat minus T2, times T2 minus T1, where the specific heat is equals to 1 kilojoule all over kilogram Kelvin for air. Now, let's proceed to process 2 to 3. Heat addition in the combustor. From our mass balance, lahat ng lalabas at lahat ng pumasok. Kaya nakuha natin tong formula equals heat added QA equals mass ng ating gas. Specific heat ulit multiplied by the quantity T3 minus T2. Okay. Sa process 3 to 4, PV and T relationship ulit in isentropic turbine expansion process. P3 P times PVK equals P4 V4K. Next, sa ating temperature naman, temperature pressure relationship. T3 all over T4 equals quantity P3 over P4 raised to K minus 1 all over K. And then temperature volume T3 over T4 equals V3 over V4 K minus 1. At least K minus 1. And then 3 to 4 nga, process 3 to 4, nandito yung ating turbine work. Equals to mass times specific heat times T3 minus T4. And then net turbine work is W sub N equals WT minus WC, or work of the turbine minus the work of the compressor. Bakit minus? Kasi mas mataas ang work ng turbine kaysa sa compressor. Kaya yan. And our cycle efficiency equals to the net work ng ating turbine over heat added QA. And that is the ideal gas turbine cycle. How about the performance of the actual cycle? This is the TS diagram, the actual cycle. So kita nyo dito, nagkaroon ng dotted lines. Yan, dotted lines. And then we have dashed broken lines. Yan. Unlike dito na constant kasi actual na siya. Hindi na siya yung ideal na value ng temperature and ng ating entropy. Okay, we have the ideal work of the compressor. WC equals mass times specific heat ulit times quantity T2 minus T1. Actual compressor work. WC A, meaning actual. Mass times specific heat T2 prime minus T1. And heat added in the combustor, QA. Mass ng ating gas, yan. Specific heat times quantity T3 minus T2. Heat supplied by fuel, yan, QF. Mass ng fuel natin, and then QH. Okay. Ideal turbine work. W is Ti sub Ti equals mass times specific heat times quantity T3 minus T4. And actual turbine work is equals to WTA minus equals mass times specific heat times T3 minus T4 prime, or work ng ating ideal turbine work times yung efficiency ng ating turbine. Okay. The ideal turbine work is equals to mass times specific heat times quantity T3 minus T4. The actual net turbine work natin, okay, it is equals to mass times specific heat T3 minus T4 prime. Yan, actual kasi ito ideal lang. Yung actual, merong konting nagkaroon ng changes dito na ideal. Yun. Sa thermal efficiency, we have the W's of TA. Ito yung actual turbine work natin minus the actual compressor work minus the W ox all over QF or yung ating heat ng fuel. And overall thermal efficiency is generator output over QF. And the compressor work efficiency is equals to T2 prime minus T1 over T2 minus T1. Okay. And the combustor efficiency naman, we have the E meaning EN, combustor efficiency, EH pala. EH, combustor efficiency, Q air over Q fuel. And the net plant heat rate natin is NHR 3,600 over efficiency. Overall efficiency, rather. Okay. Okay, let's proceed to our sample problems. A gas turbine power plant operating in an ideal Brayton cycle has a pressure ratio of 8. Pressure ratio natin. The gas temperature is at 300 Kelvin at the compressor inlet and 1,300 Kelvin sa turbine inlet. Using the air standard assumptions, determine A, the gas temperature at the exits of the compressor and the turbine, B, the back work ratio, and C is the thermal efficiency. Okay. The air temperatures at the compressor and turbine exits are determined from isentropic relation. Process 1 to 2, isentropic compression of an ideal gas. So ito yung ating formula na ginamit. Process 1 to 2. T1 equals 300 Kelvin from our steam table. H1 is equals to 300.19 kilojoule over kilogram. Okay. For the pressure one, 1.386. So, okay, now we define the value. Then PR2 is equals to P2 over P1 to PR1. So, substitute lang, and then laruin ang formula is equals to 8 times 1.386 plus 11.09. So, hanapin natin yung ating temperature 2 is equals to 540 Kelvin at compressor exit, and from our steam table, 544.35 kilogram. Next is the process 3 to 4, isentropic expansion of an ideal gas. T3 is equals to 1,300 Kelvin. And okay, hanapin natin yung value. Is equals H3 or enthalpy 1,395.97 kilojoule over kilogram. PR3 is 330.9. Okay, from our formula ulit, PVT relationship, ito, substitute natin ang laruin ng formula, 1 over 8 times 330.9 is equal to 41.36. T4, 770 Kelvin, yung turbine exit natin. Temperature ng turbine exit. Okay. And to find the back work ratio, we need to find the work input to the compressor and the work output of the turbine. Work input ng compressor natin is equals to enthalpy 2 minus enthalpy 1, 544.35 minus 319 is equals to 244.16 kilojoule over kilogram. And the work ng output ng ating turbine is enthalpy 3 minus H4, enthalpy 4, so being 1,395.97 minus 770 89.37 is equals to 606.6 kilojoule over kilogram. Okay, to find the back work ratio, work input ng compressor and work output over work output ng turbine. So 244.16 and over 606.60 is 0.403 or 40.3, 0.403 lang. Next, the thermal efficiency of the cycle. The thermal efficiency of the cycle is the ratio of the net power output to the total heat input. Net power output, W net, over QA. Okay. Q in, H3 minus H2. And substitute the value, 1395.97 minus 544.35 is equals to 851.62 kilojoule over kilogram. And then the ating work net is W out and work in is 606.60 minus 244.16 equals 362.4 kilojoule over kilogram. Thus, ang ating thermal efficiency is yung ratio nga ng net power over total heat added, 362.4 over 851.62 is equals to 0.426 or 42.6%. Next problem, okay. There are required 2,200 kilowatt net from a gas turbine unit for pumping a crude oil. Okay. Air enters the compressor at 100 kilopascal at 280 Kelvin, and the pressure ratio RP is equals to 10. And the turbine section receives the hot gases at 1,100 Kelvin. Assume the closed Brayton cycle and determine the required airflow. Airflow, meaning natin yung mass. Okay? Ano pwede natin gamitin? Yung ating PVT relationship in the isentropic compression. Okay? T2 over T1 equals T2 over T1, T minus 1 over K. So ating D2 is 540 and T4 natin is 569.74. And ang ating heat added ay 562 kilojoule over kilogram, and heat rejected is 291.54 kilojoule over kilogram. Okay, thus equals mass times 271.33. Ang ating required airflow is equals to 8.11 kilogram per second.